Let's take a moment to talk about multiple particles and the idea of entanglement. So let's consider that we have two particles that have spin. So in fact, let's just call them particle A and particle B. And actually, let's take them both to be spin up. So I'll both represent them as the up ket here. And the question we want to ask when we're talking about multiple particles is, how do we write the total state of both particles? So the total state including particle A and particle B together. So just to remind you, when we're talking about states here, we're talking about states, not wave functions. You will sometimes hear people talk about the wave functions when they're really talking about a ket, and they really mean the same thing. They really mean a state. So how do we write this total state? Well, what we're going to do is actually we just write the total state as the product of the individual states. Maybe that wasn't obvious. Maybe we could have written it as a sum, but it turns out we're going to write it as a product. Mathematically, this is actually a direct product of the Hilbert spaces of particles A and B, but we're not going to really need too much about that just to get to the basic idea of entanglement here. How about another example? Let's consider the case where we have particle A spin up and particle B spin down. What is the total wave function in this case? Well, particle A has a spin up ket, particle B has a spin down ket, and so the total wave function will be particle A up times particle B down. Notice that at the moment I'm just labeling the kets here with a subscript A and B just so I know which one I'm talking about when I'm labeling them. How about the state corresponding to particle A spin up and particle B spin right? So now it's not in the same direction. It doesn't have a spin in the same direction. Well, we can still do this the same way. We can write particle A as a spin up ket, particle B as a spin right ket, and then the total wave function, or the total state, is the product of those two. We can actually write the spin right ket in terms of spin up and spin down for particle B, because we know how this works. And so if we multiply that out, we find that the total wave function is actually the sum of two terms when I write it in the spin up and down kets. It's the sum of a term with both spin up and a sum of a term with one spin up and one spin down. Okay, so that's how we can describe multiple particles that have spin, for instance. Let's now talk about the cases where the total spin of particles A and B is 0, and we want to construct what possible states could this be. So all we know is that the two particles are constructed so that the total spin in the z direction is 0. So what are some possible states? Let's write some down. Maybe one that comes to the top of your head right away is particle A is spin up, particle B is spin down. The total spin is 0, and so that looks like it works. Of course, we could switch those. Particle A spin down, particle B spin up, and that still works. That is a possible state in which the total spin is 0. How about this one? How about the one we had at the end of the previous slide, where we had particle A spin up and particle B spin right? Well, we can see that we write this as the sum of two terms, one of which is both particles with spin up, and one term in which one of the particles is spin up and the other is spin down. Unfortunately, in this particular state, there's a chance that we would find both particles spin up. And so this can't be an allowed state for the physics that we wanted, where the total spin was 0, because there's a chance that both particles would have spin up. But that does make me think of another way of writing this down. Why don't I just flip the signs, or rather flip the spin on, say, A on the first term, or rather, I'm just going to write it like this. So the total state is the sum of two terms, where the total spin of each term is 0. So I have the sum of two terms where it's spin up times spin down, plus spin down times spin up. And this is a new kind of object from one of the ones we've written before, because each individual term can be written as something of particle A times something of particle B, but the total wave function cannot be written as a wave function or a state for particle A times a state of particle B. And this is actually the essence of what is called entanglement. So the idea of entanglement is that I write down a state that cannot be written as the product of individual states. So I can't write this as some overall state of something times for particle A times the overall state of something of particle B. Maybe that's not immediately obvious to you that you can't write it that way, but it turns out you can't. This particular state cannot be separated out in that way. So we would say that these particles in this state are entangled. Now, entanglement leads to some rather strange physics, as you probably have heard. And so we're going to talk about the classic experiment that, say, Einstein thought of on why this seems crazy, and it turns out that it's exactly what we measure. So the idea is to take two particles that have been entangled so that the total spin is 0. So we have this state which is entangled, and Einstein is going to make a measurement of the spin of particle A over on his end of the experiment. And as he makes that measurement, well, there's a 50% chance that Einstein's going to get spin up and a 50% chance that Einstein's going to get spin down. Because we see that we have an equal mixture in our wave function of particle A being in spin up or spin down. Let's say he measures the first one and he gets a spin up. So he had a 50% chance of getting spin up to begin with, but now that he's gotten spin up, we actually now know with certainty that particle B is spin down, because that is exactly what the state is that's attached to spin up for particle A. So this is the weird part of entanglement. I made a measurement of particle A, and the result of that measurement was random. I could have gotten 50% up, 50% down. But once I get that measurement, I know what the state of particle B is now, with certainty. So I now know something about particle B that I didn't know before by doing this measurement. And that's a big deal in quantum mechanics. When what we know and what we don't know, it actually seems like we know a lot less than we would like. Except now this is a weird effect of quantum mechanics giving us knowledge, more knowledge of something than we thought we would have had. Alternatively, let me imagine that Einstein made a measurement and got spin down. And there's a 50% chance of that happening. And we now know with certainty that particle B is spin up. So this is a feature of entanglement, which is that the measure of one particle affects the measurement of another particle, even if it's very far away. So I could imagine separating these particles by the size of the galaxy before making a measurement. And then Einstein makes a measurement on one side of the galaxy and gets spin up for particle A. He now knows that on the complete other side of the galaxy, right now, at this very instant, that particle B is spin down. And particle B, it turns out, is spin down. You can do this experiment, and you can see, do the particles, when you make these measurements, when you make a measurement of particle A, does particle B actually become that state? And it turns out the answer is yes. It's very strange. This does seem to violate the speed limit of the universe, which says that nothing can travel faster than the speed of light. But we have to be a little careful about what that means. So what it really says is that no information can travel faster than the speed of light. Well, in this case, it's not clear that information is traveling faster than the speed of light, because Einstein can't use this to send a message to the person on the other side of the galaxy. Einstein's measurement of measuring the spin of particle A is a random measurement. 50% of the time you'll get spin up, 50% of the time you'll get spin down, and he has no control over that. And so there's a random choice that's being made, and on the other end, for particle B, it will look just as random. Now, it turns out that they're actually correlated in a way that's determined by entanglement, but it will look correlated, and it will be correlated across these distances, but you wouldn't know that until you actually got back together. So you can't really use this to send a signal. And so in that sense, it doesn't violate the speed limit of special relativity. Okay, so I hope this gives you some idea of what entanglement is and why it's so weird.